Alright, so let's look at one more example of something that we really don't know how to do. So I could have something like, and we'll use y's again, y double prime, let's do, say, minus x squared y prime plus y, and we'll make it easy on our, well, actually we could even do something like this, equals, and let's put x cubed here like that. Okay, so we've got equals x cubed. So definitely we don't know how to do this problem, and let's use y of 0, we'll use 0 on that one again, and we'll use y prime of 0, and we'll just use 1. Not sure where this is going, just made this up. And but we can use our series to sub into this thing. Now I'm not going to go through all that series part again, so I've got y double prime, so this is the sum, k equals 2 to infinity, a sub k times k minus 1, x to the k minus 2. Minus, we've got an x squared out here this time, times our y prime, k equals 1 to infinity, a sub k times k times x to the k minus 1, and then plus the sum k equals 0 to infinity, a sub k x to the k, and equals 0. So this so I'm going to try to get everything to the j's again, x to the j again. And so once again, I'm going to do j equals k minus 2, k equals j plus 2. So here I have my sum, j equals 0 to infinity, a sub j plus 2 times j plus 2 times j plus 1, x to the j. Now here, notice that actually I've got this x squared. So x squared times each of these, it's going to add 2 to this k minus 1 exponent. So really what I have here is x to the k plus 1. So here I'm going to say, let j equal k plus 1. And so I'll have my minus again. So minus the sum. Well, if k is 1, j is 2. So this is j equals 2 to infinity. Well, j is k plus 1, so k is j minus 1. So we get a j minus 1 times j minus 1 times x to the j, and then plus the sum j equals 0 to infinity, where I'm just switching the k's to j's, x to the j equals 0. Oh wait, equals 0? No, equals x cubed. I'm sorry. Equals x cubed equals x cubed. So now, putting this all together, notice here I've got j equals 2. So I'm going to have to start with the j equals 0 and j equals 1 all by themselves. So j equals 0, I would have an A2 times 2 times 1, x to the 0. And over here, I have an A0 times x to the 0 plus A0. So I have that as my j equals 0 plus, when j equals 1, I have A3 times 3 times 2 times x to the j, or x to the 1. And then plus A1 x. Oops, got the thing too close again. So I have that. Now I'm up to the J2 and higher terms, so plus the sum J equals 2 to infinity. And now I'm going to put all those things together, so I have my J plus 2, J plus 1, A, J plus 2. So you see this gets just long and tedious. Then I have a minus J minus 1, A, J minus 1 for that, and a plus A, J. So I have all of that times x to the j. And then this whole thing equals x cubed. Okay, now, similar to when it was equal to 0, we just match up terms again, and notice there's only an x cubed over here. And so I do have that 2 times a2 plus a0 has to equal 0. So that's that term. Then the x term has to equal 0, so I have 6a3 plus a1 is also equal to 0. Then I have the x squared term. That term, so x squared, that's j equals 2, that would be 4 there, 4 and 3 more, that's 12, so I'd have 12a4 minus, and again, this is our j equal 2, so I get 1, so minus 1a1, and then plus a2 is equal to 0. Okay, because that was the x squared term. So see, here's j equals 0, j equal 1, j equal 2. But now when I get to j equals 3, that's the cubed term. And so when j equals 3 in here, I have 5 times 4, so 20, a5 minus, again, 3 minus 1 is 2, and that's 2, so that's 2a2, and then plus a3, that one equals 1. And I'll go one more here to j equals 4, and with j equals 4 I get 6 times 5, so that's 30, a6 minus, and then I'll have a 3a3 for that middle term, and then plus a4, and that equals 0 again. So as I go to solve these, right, I know that a0 was equal to 0. We had that up here as the initial conditions, right? And then a1 is, quit that, a1 is 1. And then we have, from that, then we have that a2 is equal to minus a0 over 2, which is 0. a3 is equal to minus a1 over 6, Oops, A1 over 6. Well, that's minus 1/6, or it might be helpful to write that as 3 factorial. We'll see. A4 is equal to A1 minus A2 over 12. Well, A2 was 0, so this is just 1 over 12, which is equal to 1 over 4 times 3. So, you know, maybe that's good to write it as, or 3 times 4, but I don't know. Then we can go to A5. A5 was 2A2 minus A3, whoops, divided by 20. Now A2 was 0, so that's not there, and then A3 was minus 1 over 3 factorial, and this is minus A3, and so I've got a 4 and a 5, and so that's 5 factorial, so this will be 1 over 5 factorial. A6 is, I have 3A3 minus A4 over 30. Well, let's see, A3, so 3A3, okay, that's minus a half, and so this is minus 1/2 minus 1/12, all divided by 30. What the heck is that? That's 6/12 and 7/12. So that's minus 7, and 12 is 3 times 4, and then 30 is 5 times 6. So that's 3 times 4 times 5 times 6. Well, that's almost 6 factorial. If I write this as 6 factorial on the bottom, I need to put a 2 on top. So this would be like minus 14 over 6 factorial. Don't know if that's the best way to write it or not. Now, we really need to keep going to try to discern a pattern if we can find one. But what I am noticing is it looks like the odds, right? I've got the 1, then I've got the minus 1/3, 1 over 3 factorial. Then I've got the positive 1 over 5 factorial. It looks like maybe odds are sign again. Okay, and then evens, well, evens, it started out with the first two as 0, so 0 for A0, 0 for A2. Then once I get to A4, right, I have, well, see this 1 over 12, that was almost 4 factorial. If I wrote that now in hindsight, if I wrote that 2 over 4 factorial, then I had a 2 over 6 factorial, but a 7. So I'm not sure exactly what's going on, but it looks like it might be something like, you know, 2 over k factorial, where k is even. Okay, and then with some other constant, right? Some other a in there. You know, here it was 1, then it was minus 7. I'm not sure what that's doing. So really, you know, I am kind of stuck. I could just write these terms out. And again, they started at A1, so that's an x, and then the A3. And so if nothing else, right, I can write that y of x, its first few terms are x minus x cubed over 3 factorial. I got to go up for the 4. That was the, well, I'm going to write it as the 2 over 4 factorial. So plus 2x to the 4th over 4 factorial. And then plus x to the 5th over 5 factorial. And then minus 14x to the 6th over 6 factorial, and then it keeps going with something, but I'm not sure what. So there are my terms. And like I say, in the odd terms, I kind of see a sign of x. In the even terms, I don't know, I see something that maybe looks similar to a cosine, but I'm not sure exactly what. Don't know. Now, how could I check? Well, if I knew how to solve this up here, you know, I could check the answer that way, you know, solve it. Well, if I knew how to solve it using one of our other techniques, I could, but I don't. And so this is the best I can do. Okay, but here is an example of a problem that we have not yet been able to solve, but we could solve this way. And so here's our solution, at least the first few terms of it, and that is the idea, again, for an example of solving a differential equation using series. And we're kind of sticking with these second order ones that we've done. We could do first order, we could do 10th order. They all work the same way. You just have to plug everything in and then painstakingly match up the coefficients. But there you go. This is another example of using series to solve a differential equation.